Thanks a lot for the nice introduction. And hello, everyone. Today I'm presenting our work, OptiPIM, on behalf of my co-first author, Minxuan, and the rest of the team at ETH Zurich, University of California, San Diego, and Illinois Tech. So before we dive into details about how we generate optimized mappings for processing in-memory architectures, it's also important to understand why we would like to do processing in-memory computations and how the computations are actually conducted in the memory system. So, as we all know that we are facing more and more intensive computation requirements from tensor programs like large language models or generative AIs. So of course, we would like our hardware accelerators to perform better and better. Then how good are we right now? Well, on the processor side, the hardware flops scale at 3 times every 2 years. However, on the other side, the DRAM and interconnect scale at a much slower pace, which means the performance bottleneck is actually increasingly shifting to the memory bandwidth side. And this is the well-known memory wall problem. So the most intuitive way to solve this problem is to directly put compute where the data already is, which is the key idea behind all the PIM architectures. And this kind of method is actually very effective for memory-bounded workloads. However, having efficient hardware itself alone is not enough. To achieve high performance, we also need to answer a critical question: how to map the tensor programs onto the targeting PIM architecture. And this is exactly what we're answering in OptiPIM. Now, let's take a look at what do we actually mean by mapping tensor programs. So for the one-dimensional convolution example shown here, which is composed by 2 nested loops together with a very simple final statement involving 3 arrays, each one of them are indexed by the loop variables in the nested loop. For example, if we want to map this very simple kernel onto the processing using memory digital PIM architecture, for example, SIMDRAM, which directly conduct computation using memory cells by modifying the peripheral circuit of DRAM banks. And this type of PIM devices require a special vertical layout, which means we need to lay out different bits of the same data elements vertically in one column to enable bit serial computation. And for the actual mapping of the workload, what we can do is we can simply ping all 4 filter values, like required from the workload, in one row to maximize the reuse. And then we can put another convolution window in another row, like shown here, I0 to I3. And this can generate all the partial results for output 0 in one computation step, like the schedule we're showing here. And if we keep following this schedule or this layout pattern, we can actually finish all the required computation in 8 computation steps. But of course, as user or designer, I care more about what's the actual performance resulting from this layout pattern. And there are multiple components we need to consider when evaluating the final performance. The first one, of course, is computation. And for tensor programs, we care about 2 parts, multiplication and reduction. If we assume that for multiplication, it will take 100 clock cycles in the bit serial manner, we will need to do 8 of them resulting from this layout pattern, so it will take 800 clock cycles. And SIMDRAM cannot directly do inter-column final result reduction as the pattern shown here, so there's no reduction happening directly inside the memory bank. We need to read them out to do it somewhere else, like in the host. So besides that, to start computation in the bank, we also need to load the input. This will incur some of the input loading cost. And as I have explained, that to do the final result reduction, we need to send out all the partial results to the host for the reduction. So this will also incur some of the output reduction cost. Now, let's ask ourselves a question. What will happen if we slightly change the layout pattern? For example, if we replicate more filter values in one row to enable more parallelism, this will, of course, consume more input values and in turn generates more output results in one computation step. So the second layout pattern will actually result in the schedule we're seeing here in the bottom table. And if we evaluate again the performance, this time we will need 500 clock cycles, like 4 multiplication plus 2 reductions, together with the corresponding input loading and output transmission costs. Then it's very clear that if we sum up the value, clearly the second schedule performs better than the first one. Then, is it always that simple for this layout problem that more parallelism will lead to better performance? Unfortunately, not really. As we can directly see from the schedule and the performance evaluation here, that it's already a complicated trade-off between computation and communication. Then let's take a look at another type of digital PIM architecture, near-bank processing, where the computation are not directly conducted using memory cells, but conducted in a separate processing element very close to the bank, like the SIMD near bank unit shown here, if we evaluate again the same two layout pattern as we see in the previous slide, so we don't need to worry about all those like complicated details, just focus on the red part that highlights the major difference between the architectures. So the first difference we have, like we see the cost for multiplication and reduction, we can clearly say that because we do it in a separate PE, instead of doing it in a bit serial manner, it's much faster now. We can finish the multiplication and reduction in one clock cycle. And one more thing is that since we're doing it in a PE, we need to load filter before we start computation. This will incur some of the filter loading costs highlighted by the red line here. Now, if we check again what's the final performance, then interestingly, for the same two layout, in a different architecture, now the first one performs better. Then, what are the high-level takeaways from this like seemingly complicated motivating example? Well, there are two. First one, in digital PIM, data layout is actually the first-class design decision. It dictates the schedule and in turn determines the final performance. And secondly, we're facing complicated like trade-offs between architecture and workload-specific details. Then this generally breaks down the first question we asked, how to map the tensor programs, into two sub-problems. First one, how can we describe the layout information with high-level code? As we can directly see that, nested loop is a very concise and nice way of representing software-related information. If we can somehow encode the layout information we care about, that will be a big plus. And secondly, how can we automatically explore the architecture-specific and workload-specific trade-offs to generate the best mapping? Then this comes to our proposal, the OptiPIM infrastructure, where we're taking a tensor program, unmapped version, described in nested affine loops, and we transform it into the mapped version for the targeting PIM devices. And for doing so, and to solve those two problems, for the first one, we first propose a layout-aware representation that captures both the software information and hardware-related information in a very concise and compact way. And secondly, as we want to do things automatically, and to answer the second question, we propose a general mixed integer linear programming formulation with architecture-specific cost modeling to automatically generate the best mapping based on our cost modeling. And of course, everything is open source. We implement most of the things in MLIR together with a cycle-accurate simulator adapted from Remulator 2. And now let's take a look at what do we actually mean by layout-aware representation. So for the input workload, the nested affine loops we have seen multiple times now, we will transform it into another nested loop format, like what we're showing here, which is composed by a bunch of loop levels, like those green lines you see here, 3 levels. Each one of them encodes some of the hardware information. And inside each level, we have different types of for loops, like spatial for and temporal for. They actually dictates how the data space are managed in the corresponding level. Like spatial for means different parts in the data space should be executed in parallel. And besides that, we also have those 2 lines, which is like gently ignored by previous work, the indexing function. Those 2 lines we see above the final statement. Like together with the indexing function, this actually determines what are those values actually stored in the memory banks and in which order the computations are actually being conducted. And now, let's have a look like why we call this representation layout aware. So for the outermost loop, we call it PU allocation. This level actually determines how many PUs or how many banks are actually being utilized during execution. And we can get the number of the banks or PUs directly from the loop bound. So in this example here, we have 1 times 1 bank utilized during the execution. And the second level, level 1, we call it column allocation. This similarly directly dictates how many columns are utilized in each bank during the execution. And similarly, we can get the actual number of columns from the loop bound. So in this example, we have 1 times 4 columns utilized. And then lastly, the last level, together with the indexing function, as I explained, determines what are those results actually stored in each column and in which order the computation are conducted. And the example we're showing here actually dictates the first data layout we see in the motivating example, if you still remember it. And as we already learned that this dictates how the computation are actually being conducted. Now, since we have this nice and compact way of representing the layout problem, we need, as we said, that we want to propose an automatic way of generating the final mapping. Then there are multiple steps before we can reach the final MILP formulation. The first one is we need to use a bunch of variables to encode the information we care about in the representation. The first type of information we needed is the transformed loop bounds, highlighted by the red parts. So we'll need a bunch of variables in the MILP to represent it. And the second one we care about is the coefficients in the indexing function. And after we have like variables to represent both types of information, we also need a bunch of constraints to ensure two things. First, we have a valid loop transformation. We're not doing something wrong. And second, the resulting mapping can actually fit inside the targeting PIM architecture. And with all those variables and constraints we define, we will be able to model the architecture-specific cost or performance, which will serve as our final cost function to generate the best mapping. Okay, now time to get into the complicated part. So let's take a look at what's happening actually inside the MILP. So as we have explained, so the actual thing we want to do with the MILP is to do loop transformation, like the example shown here. But of course, we cannot directly encode like 8 and 222 in a MILP. So we need an abstract view of what's happening in the MILP, like shown here. So we can abstract the transformation of loop bounds with a bunch of variables, like what we showed here. And in this work, we assume a perfect factorization of the original loop bound, and we use a bunch of binary variables to do one-hot encoding, because if it is a perfect factorization, all the transformed loop bounds can only be the divisor of the original one. And we use a bunch of binary variables to indicate which one is selected at each level. And like the example shown here in level 2, so the second one is selected, so the loop bound is 2. And of course, having the variable is just the first step. We also need to make sure that we are doing valid loop transformation, which means we need to add some constraint to specify that if we multiply back all the transformed loop bounds, they should be equal to the original one. That means we're doing the same amount of transformation, no more and no less. And when we are explaining our representation, we also said that we also need to encode the coefficients in the indexing function, like the highlighted part here. This may seem terrifying at the beginning because we may have arbitrary number of combinations for the coefficients, but actually the reality is much better. So in the paper, we have proven that for whatever kind of loop transformation you are doing, as long as you are transforming it into 3 nested loop levels, you only have 6 valid coefficients combinations, like shown here. And this finding can be generalized to arbitrary number of levels. If you're interested, please check our paper for the proofs. And similarly, we use a bunch of binary variables to indicate which combination is selected. And of course, we need the corresponding constraint that for a valid transformation, only one of them can be selected in the final mapping. Okay, then secondly, besides the property of the loops, we also need to represent a bunch of resource requirements. Because we need to make sure the generated layout can actually fit inside the targeting PIM architecture. So we need to extract a bunch of hardware information out of it. So the first one we care about is the number of banks utilized, which can be directly obtained or extracted from the outermost loop from the loop bounds, as what we're showing here. And second information we care about is the number of PUs, and can be extracted from the level 1 loop bounds. And the last one is we also care about what are those data actually stored in one column, or in other words, how many rows are actually utilized. This is slightly more complicated than the first two, as we need to analyze different arrays independently. For the filter, it's very simple because it's only indexed by one variable, f, and for output, it's the same. So for the input, it's slightly more complicated because it's actually indexed by a combination of the loop variables. And previous work directly used the multiplication of related loop bounds to get the final result. Well, this is very intuitive, but highly inaccurate. So we propose something different. So with this, we can achieve a much more accurate estimation, like the graph we're seeing here. So the subgraph A shows the result from previous estimation method by directly multiplicating the related loop bounds. We can directly say that it leads to a very high level of overestimation. And with our method, it looks much better. We achieve a 3% error rate on average for the estimation. And then, once we have all the variables we need, we also need to add a bunch of constraints to make sure that it actually fits inside. So first one we have is the number of PUs we utilize should be smaller than the available number of PUs. Second one, the number of rows and the number of columns similarly. Okay, then finally, once we have all the constraints and variables we need, we can finally start modeling the performance. So in this work, we assume the computation are conducted in the PIM unit, because this is the PIM paper, and the data is loaded from the host. And if the PIM unit cannot directly conduct the inter-column final result reduction, we assume it's conducted at the host. So as we have heard from the motivation example, we need to care about 3 parts. The first one is the computation, and we care about 2 parts, like the multiplication and reduction. Once we get a number from the representation using the variables and constraints, we need some architecture-specific unit cost for multiplication and cost and reduction from the user. And we also need to know what's the cost of input loading, and this can be obtained from the amount of the input size determined by the layout together with the bandwidth, and similarly for the output reduction. If we sum them up, simply this serves as our final cost function. By minimizing this, we can generate the best mapping for the targeting PIM architecture. And after all those like complicated and less exciting mathematics stuffs, what's the high-level takeaway from this MILP section? Well, it's very simple. We propose a general MILP formulation, providing you with all the components you need to model the architecture-specific cost. Okay, done. Finally, for the evaluation, as we said, we implemented most of the things in MLIR, like the flow showing here, and we compare the result of OptiPIM with 3 other baseline mapping methods. The first one is the weight parallel heuristic, taken directly from the HBM PIM paper from Samsung. And the second one is search-based method, PIMDL. And third one is a modified version of an ASIC targeting mapping method from COSA. And we use HBM2E as the basic configuration for both types of digital PIM devices. And for the actual evaluation, we use an analytical evaluator, which is cross-verified with our cycle-accuracy simulator. And we achieve a squared Pearson correlation coefficient for more than 0.99 for both digital PIM architectures. So in short, it's very well correlated. Okay. Then for the full benchmark evaluation, we plot the speed-up graph like shown here. And the graph is normalized to the slowest one among all 4 mapping methods. And for SimDRAM, OptiPIM achieved 2.3 times speed up than heuristic, 2 times than PIMDL, and 1.1 than ASIC. So it seems like we didn't achieve a lot better than the ASIC one. Why is that? Because let's take a look at the subgraph B. This is the breakdown of the performance. And you can see that the computation takes a lot, like part is the biggest portion in the performance. And computation is also the first-class optimization target for the ASIC method, and that's why we didn't achieve a very good speed up. And for HBM PIM, actually we did a much better job because actually both the heuristic method and ASIC one, they did not handle the combination cost very well, and our method did it much better. We also have results for ablation study and scalability, but due to time limit, I will not show it here. If you're interested, you're welcome to please check our paper. And then, to conclusion, we proposed the OptiPIM infrastructure, which proposed the 3 points as you already see here. So like a layout well representation together with accurate cost modeling and an automatic mapping generation method based on MILP formulation, and we open source the repo. Here is the QR code. If you are interested, please scan it. And then the final conclusions will achieve at least 1.9 times faster than heuristic and search-based method. And thanks a lot for listening. If there are more questions, please come to the poster session. Thanks.
Thank you, Chien-Yi. Yeah.